Thank you, everyone. I greatly appreciate you guys all tuning in for our talk. So I definitely want to thank a few people before we get started. In addition to our speaker, of course, I want to thank Eli Williamson. He's done a fantastic job contacting speakers for this speaker series and really planning everything out and making sure that we have the advertisements and everything. So I really want to thank Eli. He's done a fantastic job. And Eli, I believe, is going to be passing this off to AJ Messenger in the spring. So we're going to thank AJ in the spring, and Eli's going to help AJ get that off the ground in the spring semester. But I also want to thank the physics department and the College of Science here at Marshall University. They've always been supportive of our Society of Physics Students group here, and we appreciate everything that they do for the group here as well. So this speaker series has been funded by a variety of different places over the years. So currently it's funded by the Society of Physics Students Fund. That's an endowment set up by an external donor. So we want to definitely thank our donor for that. But we also want to thank the American Institute of Physics, also the West Virginia NASA Space Grant Consortium. These are also different organizations that have sponsored this talk over the years. And I think we started this, Eli, in fall 2020, right? So this has been going on quite some time, one talk per month during the academic semester. So I want to thank all the sponsors and Eli, and especially our speaker, for joining us today. A little bit about Marshall University. We are an R2 high research university. We are about 9,000 undergrads, 2,500 grad students. Our physics department here has about 6 people on site with 4 active in research. So if you're interested in physics or have questions about a career in physics or majoring or minoring in physics, shoot me an email. I can definitely get you in touch with the right people that'll be able to answer your questions if I can. So my email is mcbrides@marshall.edu. I'd be happy to help answer your questions. If you also want to do some outreach in STEM, we have our award-winning SPS chapter, Society of Physics Students. Just also shoot me an email, let me know you want to get involved, and we'll put you on the list and get you involved in doing some outreach in the community on and off campus. So our program here in the physics department has several different tracks, a pure track, an applied track, a bio track, a medical track, and a medical imaging track. So in those tracks, you would get a BS degree in physics, but you would also learn about an area of emphasis, such as biology or chemistry or things like that, where you would pick up a minor. So if you have other interests, we have definitely different tracks to accommodate you. And our pure physics plan is very flexible. You can also do double majors within majors within the College of Science fairly easily. And then finally, we do have 2 master's programs, a master's program in physics, as well as a master's program in physical and applied sciences. So if you're interested in pursuing a graduate level degree here at Marshall University, we can also accommodate you in that area as well. And within that applied master's program, we actually have a new program, area of emphasis for certified teachers. So that's an area of emphasis in teaching for physics. So if you're interested in any of those things, again, reach out to me at mcbrides@marshall.edu, and I will be happy to help address your questions. So with that, I think I will turn it over to Eli, and he will properly introduce our speaker.
Okay, thank you, Dr. McBride, and thank you to everybody out there joining us today. This will be the 17th talk in our Faces of Physics series, and I'm very excited to hear our speaker tell us about his career at the Large Hadron Collider in CERN and the University of Tokyo and a little bit of everything. But I'll be introducing him shortly, but I have a few quick announcements first. After the presentation, just like all the other talks, we'll have a Q&A at the end with our speaker, and we welcome and encourage you to share your questions in the YouTube live chat. If you enjoyed this presentation, we would hope that you join us for future talks in the series. I will not be hosting these anymore, as Dr. McBride said. AJ Messinger will be taking over for me next semester, as I am student teaching all next semester. So wish me luck with that. So now it is my pleasure to introduce our speaker. Ooh, I lost it. Hold on. First time this has happened. Technical difficulties. Okay. My apologies. I am not on my typical setup. Dr. Yasu Okamura has been studying experimental particle physics at the Energy Frontier Collider experiment since 2006. He completed his PhD thesis with one of the early results at the Large Hadron Collider at CERN, which measured the top quark pair production cross-section in 2012, with which he won the Atlas Thesis Award in 2013. Dr. Okamura was a postdoc fellow at the University of Chicago, working on the upgrade of the Large Hadron Collider Atlas experiment from 2012 to 2016. He has been a staff member of the University of Tokyo since 2016. Now, as an associate professor, he leads the high energy physics research activities at the University of Tokyo and at CERN. So I wanted to thank all of you for coming out tonight, and a huge thanks to Dr. Okamura for taking the time to talk about his work amidst his busy schedule. And so now I will turn it over to our speaker. Without further ado, Dr. Yasu Okamura.
Okay, so thank you very much for the introduction. And first of all, let me thank Ellie and Sean for this opportunity. And I'm really excited to have this nice opportunities for the physics talk. So let me start sharing my display from my end. Okay. Okay, so I believe I'm sharing the correct one. All right, good. Thank you very much. So today, I'd like to give a kind of introductory talk for the elementary particle physics with the title of Higgs vacuum symmetry. Let's reveal mysteries of the universe with the LHC. The LHC stands for the Large Hadron Collider. This is the world's highest energy collider running at CERN in Geneva, Switzerland. And today I'd like to share some very basic and important and interesting concept of the particle physics, which is so-called Higgs mechanism. And if you have some interest for this very, interesting concept for the standard model physics, that's the aim of the talk. Okay, let me start. So since this is an introductory talk for the particle physics, let me start. What is particle physics? Now, this is a series of studies for the elementary particles and their interactions. And this one, this is the kind of periodic table of the elementary particles that we know in the universe. Now we have three different types of the elementary particles in the table. And the first group is so-called fermion. And so as this figure shows, so we have the matter like hands, and it consists of the atom. And by zooming up the atom, we start to see the nucleus and the electron. And here the electron is already so-called elementary particle physics. On the other hand, the nucleus can still divide into the neutrons and protons. And furthermore, we have known that the proton is consisting of the quarks inside that. And we know that so far, we didn't know the constituent of quark, and the quark cannot be divided into the further elementary particle. So then we consider that the quark is the elementary particles for the matter. And here for the fermion, we have so-called quarks, and also we have the leptons. Like electron is the lightest charged lepton, and we have the three generations for leptons. And also for the quarks, up quark and down quark consist of the proton and neutrons. And we have the charm quark, strange quark, and the top quark and bottom quark, which is very similar to the up quark and down quark, but different mass. So we are calling these series as three generations of fermion. Somehow we have the same structure between the quark and lepton. And this is not the main topic for today, but this is very fundamental questions of why we have these similar structures between the quarks and leptons. And then the second group is so-called gauge bosons, which are considered as carriers of the force. So in the physics, we know that there are 4 elementary interactions, forces. They are strong force, weak force, electromagnetic force, and gravity. Since the very different feature and also the small magnitude of gravity, the gravity is not integrated in our theory of the particle physics, but for the other 3 interactions, the strong, weak, and electromagnetic force is well integrated, and all the observed phenomena can be explained by the standard model using these gauge bosons interactions. And then finally, we have the Higgs boson here. This is the only scalar particle. Scalar means a spin 0 particle in the periodic table of the elementary particles. And this has been predicted since 1964. And since then, the experimentalists kept searching, looking for the predicted particle, and finally it was observed in 2012 at the Large Hadron Collider at CERN. And in today's talk, I'd like to share why we need Higgs boson and how it changes the view of the nature, view of the universe. Okay, so for this context, let me start from what is a weak interaction. So weak interaction is one of the interactions that the standard model describes, as we discussed in the previous slide. And the weak interaction is maybe, how to say, kind of exotic interactions for you, because yeah, it's kind of hard to feel the interactions in the daily life. And the beta decay is the most typical phenomena of the weak interactions. And as shown in this figure, a free neutron will decay into the proton and electron and antineutrino with 15 minutes on average. And the 15 minutes is indeed a very slow process in the particle physics. For instance, typically we are treating with interactions within 10 to minus 23 seconds for the strong interactions. So this is very long process. And here, let me mention that the slow process means low probability of the interaction per unit time. I mean the low rate of the process. And this is the reason why it is called weak interactions. We have the low priority, low probability, and this is because the interaction is very weak. And by the way, I would like to also introduce very fundamental concept of the physics. So why the neutron will decay into proton, electron, and antineutron is that the state of proton plus electron plus neutrino is more stable than the free neutrons. This means that this state after the decay has a lower energy, and nature prefers a lower energy state. And this is very important concept if we discuss about the vacuum, which is the lowest energy state of the universe, which is preferred by the nature. Okay. So then, so about the weak interactions, is it really the exotic force? And indeed, I would say this is related to our life, actually. So, for instance, slow process of sun is owing to the weak interaction in the chain. So one of the process is originated from the weak interactions, and then the rate is very low, and then the process is slow. And yeah, thanks to that, we have the long lifetime of the sun, and we don't need to worry about the full consumptions of the energy of the sun for our time scale. And also the hot spring is owing to the energy released by the beta decay. And so this is a photo of one of the most famous hot springs in Japan. This is a Kusatsu Onsen. And yeah, so the physics research reveals that the half of the geothermal energy is originated from the nuclear interactions, and the major part of it is beta decays, the weak interaction decays of the radioactive nucleons. So yeah, thanks to the beta decay, we can enjoy the hot springs, yeah, on the Earth. So yeah, I would say in this sense, the weak interaction is kind of related to our regular life. So, and the weak force is very strange in terms of particle physics, indeed. And this is indeed the reason why we need the Higgs boson. And let me share the story of the reason why the Higgs boson is needed and how the weak force is strange. Okay, so by the way, let me start from what is a force. So, so in the physics course, we learned that the force can change the particle motion according to the equation of motion. And also, we learned that the field strength is getting smaller according to the inverse square law, like 1 over r square, as you can see here. And so I believe you learned that for the Coulomb interactions and also the universal gravitations. And yeah, this is in the in terms of particle physics, this is corresponding to the massless carrier gauge bosons. And also, in general, force does not change the so-called its terminology, but U1 gauge boson, for instance, the electric charge. And this is the basics for the force in the physics. On the other hand, the weak interaction violates these rules of the particle physics. For instance, if we draw the force strength as a function of length, then the force first following the 1 over squared r, the inverse squared law, as you can see here. On the other hand, at some point around the 10 to minus 17 meter, the force is suddenly getting to 0, like that. And so this is very different from the basic rules as we saw in the previous slide here. And this in the particle physics, it is considered that the weak force is carried by massive particle. That's very strange part for the weak force with respect to the other force in the particle physics. And also, if we write down the process of beta decay, the decay of neutrons into the proton, electron, and anti-neutron, neutrino, in terms of quarks, this is shown like here. Indeed, in the beta decay, one of the down quark is changed into the up quark, radiating the electron and the neutrino here. And in this process, the down quark is changed into the up quark, and we know that the charge for the down quark is minus 1/3, and the up quark is plus 2/3. So then this is changing the electric charge, and this was considered that a fundamental U1 gauge charge of the particle changed by the weak interactions. So this is another point that the weak force is considered to be very strange. And then from here, to solve this strange behavior of the weak interactions, we are introducing a complex scalar field. Eventually, it is called the Higgs field in the discussion. So we are introducing this complex scalar field for our universe. Then here, let me start from what is the field. So especially in terms of physics. So the field, so the definition of the field in the physics is quantity as a function of position and time, or in other words, space-time. So here I would like to share two simple examples of the field. The one of the simple example is the temperature map. So this is shown here. So as a function of, so this is only the snapshot for a certain time, but we have the evolution of time. So we could say that this is a scalar quantity as a function of time and position. So this is we can consider that the temperature map is a field of scalar quantity. And then the other example I would show here is the wind map. So we see that the arrow at each positions, and again, so we have the series, the evolution of time behind the plot. So then we could consider that this is a field of three-dimensional vector quantity as a function of time and positions. And here, so we are limiting the surface of the Earth. So it could be two-dimensional, but anyway, this is the field of the vector quantity. Okay, then what is a complex scalar? And this is the quantity. This is a quantity defined with two numbers. So we have the two representations, two typical representations for the two numbers. So one of them is the representations with real number and imaginary number for the complex scalar, like 1 plus I. So 1 for the real number and 1 for the imaginary number, and then this is shown as 1 plus I. Or in the plane of the complex numbers, it is pointed as here, real number 1 and imaginary number 1 here. And the other representation is with module or magnitude and argument or phase. So the point can be presented as this green arrow. And so this one has the length of square root 2, and the phase, the argument or phase of the quarter pi, 1 over 4 times pi, as you can see here. So yeah, this is equal number, and so we can say that this is 1.1 in terms of the first representation, or we can say that this is the magnitude of square root 2 and the argument of the pi over 4. So yeah, we have these two representations. And then, so let me come back to the complex scalar field. The particle physics often handles a complex scalar field. And so simply speaking, complex scalar field is a complex scalar quantity as a function of time and position. And the Higgs field is indeed a complex scalar field. And here, so this is a map of Japan. So excuse me. So some of the materials are originally prepared for the lecture for Japanese students. So I put the Japanese map here. But anyway, so like the weather forecast map, we can plot the complex scalar field as a function of position. So let's image like that. And here, please remember that differently from the wind map, so the wind map, the direction of the wind map is exactly corresponding to the space direction in the map. On the other hand, so this complex scalar field case, the direction is not related to the real directions of the space at all. So yeah, this is very imaginary space phase. And yeah, just for the visualization purpose, I put these things. But anyway, this is not related to the real direction there. Okay, so what this one representing is at each point we have some complex scalar quantity, and this can be shown as a arrow, the green arrow, as we introduced here. So for instance, so here, this is around Tokyo, and we have this direction as a phase, and we have this size as a magnitude of the complex number at the Tokyo. And then, so we have the Kyoto around here, and we have this complex number there, and we have Osaka here, and we have this complex number here. So this, this is trying to showing the complex scalar field in the map. And then, so of course, we don't know what is such a complex number at all around our world. But anyway, so let me share this concept. And also, I'd like to introduce our important concept of the phase symmetry. The phase symmetry is one of the fundamental concepts of the particle physics. And the symmetry here means that we don't have any preference of the phase. And this means that so equally, all phase is equally preferred by the nature. And then, so we don't have the specific phase in the complex field. So this is the meaning of the phase symmetry. And this is very important principle in the particle physics. So if we introduce some phase in the representations of the nature, we don't expect we cannot expect there is some special phase, but they should be equally preferred by the nature. And so by having such assumption, we indeed succeeded in the prediction of the elemental particle interactions like QED, the electromagnetic force, and also the strong force can be, well predicted and described with respect to this principle. However, if we assumed the phase symmetry for the introduced phase quantity, the related force should be propagated to far away following the inverse square law, and also the force related to the phase could not change the corresponding gauge charge. And then let me come back to the how strange the weak force is. So indeed, the weak force is not following the 1/square law, and also the weak force is somehow changing the electric charge. And both of them are, violating the concept of the phase symmetry, unfortunately here. So, but on the other hand, large part of the weak interaction can be described by using the idea of the phase symmetry. So what we will think here is weak force is indeed following the phase symmetry, and intrinsically satisfies the phase symmetry at the very beginning of the universe. But in our cold universe nowadays, the phase symmetry has been broken owing to some unknown mechanism, and then the weak force is the weak. the weak force is weak as it is really observed by the experiment. So we have the very progressive hypothesis here. Our university somehow eventually prefers a certain phase and violated the phase symmetry. So that's the the hypothesis here. On the other hand, we should assume that our weak force intrinsically satisfies the phase symmetry. So we need to break the symmetry somehow in the natural way. So then here, so let me repeat again. The hypothesis is we introduce a complex scalar field, and that is eventually breaks the phase symmetry. In other words, the one particular phase is favored by nature with some mechanism. And then, so to realize such universe, we have the following setup of the newly introduced field. So intrinsically, the field does not have any preference for a particular phase. In other words, the potential energy of the field does not depend on the phase explicitly. So for all the phases, we have the equal potential. Therefore, we cannot say that which phase is the lowest energy as a vacuum. However, in our setup in this hypothesis, it takes cost if there is a variation of the phase as a function of time and space. So in the mathematics, the potential energy of the field depends on the derivative of the phase, like d theta dx or d theta dt. And if we have the potential energy depending on the size of the derivative, then if we have the different phase, like here this phase, here this phase, here this phase, here this phase, that's cost the energy. Or if we have the, evolution of the phase as a function of time at a certain point, this also costs the energy. So then, so if we have such a setup, eventually, if one of the at some space point of the universe, if the phase is taken for one direction, the similar phase will be taken everywhere in the end with this setup. And this is so-called spontaneous symmetry breaking. And intrinsically, the field does not have any specific phase as a preference, but so due to the feature that the surroundings prefers the similar phase as the surroundings. Then, so eventually we have everywhere in the universe, we have the similar phase. That's the concept of the spontaneous symmetry breaking. And this is like behavior of crowd. Then, so in the hypothesis, so in the very early universe, like 10 to minus 12 seconds after the birth of the universe, we have the phase transitions of the universe happened, and then the phase symmetry was broken. So this is the history of the universe, and the 10 to minus 12 second is somewhere here. And so before that, we don't have the symmetry breaking, but somehow by having the phase transition of the space, we started to see the symmetry broken universe in terms of phase. So in other words, in this hypothesis, in the 10 to minus 12 seconds after the birth of the universe, our universe was frozen. So this is the molecule for the water. And if we have the symmetry in terms of space, so there is no preferred direction, and then all the molecule is kind of random. On the other hand, if we have the temperature low, and then so rather than keeping the randomness, they would like to have the some state with a lower energy. And then finally, we have the, I would say, some concept of the preferred directions in the system. And this is after the symmetry breaking. And indeed, this is what is happening in the phase transition of the water, and it is called frozen. And so similar things happen in the universe. So originally, we have this kind of random phase at the beginning. On the other hand, when the universe is getting colder, we have one phase is well preferred, as you can see here, and this is considered as the frozen universe in this sense. So, but how it is really happening? So we talked at some point the universe changes the state a lot, and we have the phase transitions of the behavior of the universe. How it is possible? So this is showing what happened at the 10 to minus 12 in our universe, the history of the universe. So so we have such a potential changing as a function of the temperature of the universe. And the very hot universe at the beginning, we have such potential as a function of the complex number. So here the imaginary number and the real number. And so according to what complex number was taken at a certain space-time, we can define the potential energy for the Higgs field. And then, so at the beginning of the universe, we have such a potential energy of the Higgs field. And then what happened is the Higgs field preferred the zero size of the complex number everywhere, owing to this potential shape, the shape of the Higgs potential. That's happened at the beginning of the universe. And also you can see that the potential energy is symmetric for the phase, the direction of the arrow. On the other hand, at some point, the potential shape was changed, as you can see here. So we have this kind of wine bottle shape around the complex number of zero. On the other hand, we have some lowest energy point out of the complex number with a certain size of the certain magnitude of the complex number, as you can see here. If we have this transition with the potential shape of the Higgs. And let's assume that somehow we can make this transition. Indeed, in the physics, in the particle physics, the parameter of the interactions can change as a function of the temperature, the environmental energy. So yeah, it is kind of a natural concept that how to say, the coupling constant is running as a function of energy. And so this means that, so first we have such a potential energy, and on the other hand, so having the energy, having the university corridor, then the coupling is running, coupling was changed, and then the potential shape was changed, as you can see here. And if this was the case, so after the 10 to minus 12 second, we have the finite size of the complex number. And if we have the finite size of number, then the spontaneous symmetry breaking mechanism happened, as we discussed. And then we will have eventually such alignment of the complex scalar field. If we have this really, this one is really this one, the nature has such a complex scalar field, and if we have such a phase transition happened at the very early universe. So yeah, this is very, let's say, aggressive hypothesis. And yeah, this is very interesting. And then the question is, can we prove this very attractive hypothesis? And then the answer is yes. And so how we can do? So by observing Higgs particle, we could prove this very interesting hypothesis. So up to here, I didn't say Higgs particle, but I kept saying Higgs field or the complex scalar field. And so in this slide, for the first time, I said the Higgs particle. And what is the Higgs particle and how it is corresponding to the Higgs field that we introduced as a hypothesis. So if we have such a wine bottle type potential shape of the Higgs field, then the lowest energy is some of this point here. And as we discussed, once one point takes some phase, then the surrounding space-time will follow the same direction, the same phase. And then eventually the universe will take one of the phase as a vacuum, as you can see here. The vacuum means the lowest energy, or at least the one will be taken by the nature spontaneously. And then, so if we have such a potential of the Higgs field, and so here in a perturbative way, if we see the potential, it is something like that. And this is very similar to the harmonic oscillator in the quantum mechanics. And so if you learn the quantum mechanics, we have the quantizations of the harmonic oscillator potential. And so for such a case, the nature cannot take the any numbers continuously, but only the quantized number can be taken. And here, so this is a ground state, and then this is the first excited state. And so here we have the gap, and so by exciting the vacuum, and then this can excite the Higgs field in terms of the Higgs potential. And so, and this can happen only for the certain energy because we have the gap of the energy. And so by observing this resonance type process, we can prove the very interesting concept of the nature as I've introduced. So here's a recipe to observe the Higgs particles. So we need to concentrate the energy at one point, and then this could induce the Higgs field excitation, and then so the excitation can happen only when stimulating vacuums with a specific energy corresponding to band gap, as you can see here. And this can be observed as a resonance in the experiment. And by the way, the size of the band gap is considered as a mass of the Higgs particle. And how we can do that then? So let me come back to the Large Hadron Collider. This is the most important tool for us to understand the mystery of our universe in terms of the Higgs mechanism. So the Large Hadron Collider, LHC, is the world's highest energy particle collider. We are calling this is a energy frontier collider running at CERN in Geneva, Switzerland. So here we have the 27-kilometer ring of the accelerator machine. And so at one point, indeed 4 points, but anyway, we have the so-called collision point, and the accelerated proton, the bunch of protons and bunch of protons are crossing at the interaction point. And then we are observing what is happening there with a series of sensors located at the crossing point of the proton bunches. So here we have the head-on collisions of the high energy protons to excite the vacuum in the laboratories. And in the design of the LHC, we have the energy of 7 tera electron volt TeV and 7 tera electron TeV from the other side. And by having the head-on collisions, we have the 14 TeV in terms of the center of mass. And so this 7 TeV is very high energy if we are considering the energy of a single particle. And this is corresponding to the 2.7 times 10 to 14 of the kinematic energy of the molecules in the room temperatures. And by having such a high energy protons, we may excite the vacuum, and we may observe the resonance process corresponding to the Higgs particles. So that's the recipe of observation or proof of the mechanism of the Higgs. And then, so the band gap size cannot be predicted before the observation, but so by having the if we assume a certain number of the band gap, then we can calculate everything by using the standard model framework of the particle physics. And so for the typical case, so before the observation, we already have the prediction, and the excitation of the vacuum field would be expected to happen with a probability of 10 to minus 9. So we had a good chance to observe that if the nature really took the super attractive hypothesis as I introduced in the previous slide. So let me share some fun movie, which is provided by Sun. So this is the accelerator complex of the Sun, and this starts from the hydrogen, and we have the series of the injector accelerators to finally accelerate the protons up to the 7 TeV. We have the LINAC, PS booster, proton synchrotron, SPS, and finally the particle is injected into the Large Hadron Collider and accelerated up to the 7 TeV, and then finally it's colliding in the center of the detectors to excite the vacuum. Okay, so then so we have the so-called detector to observe what is happening in the collisions of the high energy protons. So what is happening here is we have the large number of proton colliding in the center of the detector, as you can see here. And we have the layers of the sensors so that we can measure the outcoming particles type, energy, and momentum. And then the excitation, so if we had the excitation of the Higgs field, and it will decay immediately after the excitations. And for instance, so this is a decay of the Higgs particle into the 2 photons, Higgs to gamma gamma. By the way, this is a Japanese character for the photon or light. And then so we cannot observe the Higgs directly, but the photon as in the final state can be observed by the Atlas detector. And so we should remember that this is a resonance process, as you can see here. So by collecting such candidate event, and if we see the bump as a resonant process, we could confirm that there is something more than just a simple vacuum. So that's the logic, how to observe the Higgs boson. So typically, we have the Higgs to 2 photon process, and also we have the Higgs to Higgs decaying into the 2 G bosons, and then the G boson will also decay into the other particles immediately. And with respect to the, how to say, clear signature in the detector, the electron, and muon final state. It is shown here. Higgs to GZ and mu final state is one of the important processes to observe the Higgs resonance. And this is one of the candidate event of the mu. So similar to the color here, we have the 2 muons, and also we have the 2 electrons in this collision event. This is indeed the real event, and this presentation is, this way of the presentation is so-called event display. And then, so to observe the Higgs, we repeated the collision event really a lot and accumulated the data, as you can see here and then. Finally, with a certain amount of the data, we observed the bump for the Higgs to gamma event, and also the Higgs to for lepton, the mu EE or mu or EE event, as you can see here. So, excuse me. And here for the observations, let me remind you that the statistics is very important, because we have to rule out the case of chance coincidence. So the probability of the chance coincidence is conventionally required to be less than this 0.000057% to claim a solid observation. And to do that, we had a lot of collisions repeated to confirm the observation. And so this is captured from the movie in the previous slide. And left one is as of October 2011, corresponding to the 5 × 10⁻14 collisions. So indeed, we should have the Higgs event here. On the other hand, we did not see the clear signals, because we have the statistical fluctuation, and we cannot say that there is the solid observations. On the other hand, by having the 25 × 10⁻14, finally we have this clear structure on top of this smooth falling background. And this is really the feature of the resonance effect. And then we can clearly claim that there is a Higgs observations. And by the way, so to have that, we have 20 collisions per every 50 nanosecond in the 2012 LHC operation. And then also, we found that the measured rate of excitation and the decay of the excitation is exactly as expected for the frozen vacuum and the universe with spontaneous symmetry breaking mechanism hypothesis. So yeah, with the experimental data, we could probe really the hypothesis is taken by the nature. So that's very interesting things. And then also, after the observations, we keep accumulating the data. And so as of 2018, we collected 150 × 10⁻15 collisions have happened. Let me see, this is really correct. 20. I think, yeah, the one order was wrong. But anyway, so we have a lot more the proton-proton collisions since the Higgs observation. And indeed, in the operation with 2018, we have 55 collisions on average every 25 nanoseconds. This is a lot, and this was very challenging operations of the experiment. And with this huge statistics, we can reveal a lot more things for the Higgs particles, the nature of the Higgs field, and the various coupling of the Higgs particles to other particles has been confirmed by the actual experimental data. And this is the so-called Higgs coupling plot. This is very important plot from the LHC LAN2 data taking. And yeah, we have the various standard model particle, and we confirmed where we saw the evidence of the interactions with Higgs for each particles of the standard model as shown in this figure. And this was the meaning of this plot is the interaction coupling is really as expected in terms of the hypothesis of the Higgs mechanism. And then with the recent data, we observe the not observed, but we saw the very significant result, which suggests this Higgs to mu decay, as you can see here. And since muon does not have the large coupling, we expected the decay rate is very low, like 0.0022%. So the probability of the Higgs excitation is already very small, but the branching, the decay probability is further small. So yeah, we have the very little chance to see these things, but thanks to the very large statistics of the LHC data, we started to see the evidence of such process already. So by compiling these observations, we confirm that the symmetry breaking nature of our universe and the vacuum by the actual experimental data. In other words, it is experimentally confirmed that you are surrounded by spontaneously symmetry broken complex scalar field. So yeah, as I showed, so somehow we have such a complex scalar field around us, and this is what the nature took. And then, so after the observation, we have the further understanding of the Higgs potential with the experimental data. So now we can do some study of the vacuum stability. And so with the experimental observations, we can extrapolate the Higgs coupling to the back to the early universe. And by analyzing that, we saw that indeed at some point the Higgs potential is have the very unstable shape, possibly. And then, so this means that at the very beginning of universe, the universe could be very unstable, or maybe we could say that, so our potential of the universe, the Higgs potential have such shape, like we have some true vacuum, true lowest energy state, which is different from our universe. So this was suggested by the recent data of the Higgs study. And yeah, there are a lot of things more to understand around the Higgs mechanism after the observation. So then finally, this is summary. So today I introduced very exciting and interesting hypothesis of the symmetry breaking of the universe. And the particle physics built and established this very interesting, exciting idea about our universe with a complex scalar field spontaneously broken at the very beginning of the universe. And yeah, it was happened at the 10 to minus 12 after the birth of universe. And interestingly, the Collider experiment can see the evidence of this hypothesis clearly. So, and then, so I would like to say that, so it's not the end of the story, but there are a lot of unknown things in the universe still. So we don't know what is the physics before the 10 to minus 12 second yet. And also the Higgs vacuum stability is a very interesting topic. Now with respect to the large amount of Higgs data. And so still there are a lot of interesting mysteries, and we have a lot of homework for the next decades. So yeah, if you are interested in, let's reveal mysteries of the universe with LHC or maybe other energy frontier machines on the Earth together. All right, thank you very much. That's it.
Okay, thank you very much, Dr. Okumura. I really enjoyed it. I thought it was a great talk. Definitely lots of high-level physics stuff, and I had just recently learned about some of this stuff in my Introduction to Modern Physics course, so I was familiar with a good amount of it, but. Okay, so we're going to go ahead and open up the chat for questions. If there's anybody that's watching that has any questions that they'd like to ask Dr. Okumura, go ahead and do so. But I haven't gotten anything in here yet. So I wanted to go ahead and ask, how did you get started in particle physics? Like, when did you gain your interest in it?
Yeah, that's a good question. So when I was a third year of the undergrad student, we had a seminar to discuss about the particle physics. And then, I learned that how to measure, how to observe the Higgs boson, and how to confirm the Higgs mechanism is really what the nature took. So that's before the Higgs observations. So we don't know what is the band gap of the Higgs, and we don't know if this is really what nature took or not. So then, and also, I cannot believe that there are some kind of complex scalar field around me, but that's very interesting to me that that can be seen by the actual experimental data, and this was really attractive. So then I decided to start the particle physics at the time.
That seems to be the general consensus whenever I ask that question is, well, I heard about something, I thought it was interesting, and I wanted to figure it out. So I think that's kind of the heart of science. So it's great to hear.
Yeah, indeed. Once I started, so it was very fun for me to do the experiment. So yeah, the beginning of the first motivation is the interest, but then the motivation to keep studying the physics is indeed it was fun for me. So
it's actually it's interesting that you mentioned that, because I'm currently working on my capstone project for I'm an education major, physics education, and I'm actually doing my capstone presentation next week on the fun of physics and how that affects students' learning. So I'm very glad that you mentioned that, because I have been researching it over the past semester. So
great.
Well, it doesn't look like we're getting any questions in the chat. I did want to tell you, Dr. McBride said that he apologizes. He had to leave. He had a faculty senate meeting, as he mentioned before the talk. But I'll give you his email afterwards, because he said he wants to stay in touch. So, all right. Well, there are no questions in the chat. So I think I'm just going to go ahead and end the live stream here, and then you and I can talk for a second. All right. Well, thank you for everybody that watched. Thank you again, Dr. Okamura, for your talk. And okay, it's ended. So as Dr.